Good morning, Pirates. Today we're going to talk about something called intermolecular forces. They are abbreviated as IMFs. Okay? Intermolecular forces are the forces between two molecules, just like interscholastic sports are between two different sports teams, like Palatine against Fremd. Okay, there are 3 steps to determine intermolecular forces. Let me go through the steps with you, and then we will go through some examples. The first step is to determine the type of bond you have based on electronegativity. So this is from last part of this unit when we were trying to figure out if a bond is polar, greater than or equal to 0.5. Then we have to look at whether or not the entire molecule is polar, not just the bonds, but the whole molecule structure, okay? And this is going to be based on vectors, which I'll go over in our examples. We're trying to see if that polarity cancels out. And then your last step is going to be to determine what type of intermolecular force it has. Okay? In our covalent unit, there's really 3 types. Hydrogen bonds, dipole-dipole, and London forces. Okay? We already talked about ionic in our first semester unit. Ionic is the strongest type of intermolecular force because you actually have a transfer of electrons. So you don't have just partial positive and negative ends, you actually have a true positive and negative end. Something to write down here is that the strongest forces are at the top. Okay, so they are ranked in order. Ionic is the strongest, hydrogen bonds, then dipole-dipole, and then London forces. So let's talk about how we actually see some of these. Okay, I would like you to add a little bit of notes here. If you have a polar bond, okay, and you start looking at the molecule, if the vectors don't cancel out, which I will show you in our example, then the entire molecule is polar. And then we're either going to have something called dipole-dipole or hydrogen bonds, and I'll go through the difference there. Hydrogen bonds are when you have hydrogen bonded to nitrogen, oxygen, or fluorine. And if you have a polar bond, however, the vectors do cancel out or cancel each other, then it's going to be a nonpolar molecule. And like I said, we're going to go through some examples. Okay, let's start with our first one here. Okay, we have CH4. Okay, last section we practice whether or not the bond is polar based on electronegativity. Okay, if we look at our periodic table and we find carbon over here and hydrogen over here, remember hydrogen is a nonmetal, the electronegativity values are in the bottom corner. So we have 2.5 and 2.1. If we take 2.5 minus 2.4, we get the difference is 0.4. Which means these are non-polar bonds. So even if we look at the electronegativity value, it looks like carbon wants the electrons a little bit more because it's closer to filling its octet. Carbon might have this partially negative end of the molecule. And so we have something here called London dispersion forces, which is anytime you have a non-polar molecule based on non-polar bonds, because even though these electrons are being equally pulled in towards the more electronegative element, towards carbon, remember electrons are constantly in motion and they move almost at the speed of light, so they're super fast. So as they're moving, they can sometimes create, temporary dipoles. And what I mean by that is if we had another CH4 molecule next to it. And let's say for now, in this molecule, there's a partial positive towards hydrogen since the electrons are going towards carbon. However, at that given moment, let's say these electrons are moving in this direction, and we have a partial negative on this end. We know positives and negatives attract. However, this attraction is kind of temporary, right? Because the electrons are going to keep moving, and then the poles, the polarity and the different positive and negative will move around. All right, let's look at our next scenario of when we have a polar bond. Okay, so if we look down here at this molecule, we have carbons and hydrogens like we did up here, and we know the carbons and hydrogens have nonpolar bonds between them because their electronegativity is not a great difference. It's 0.4. However, we have this carbon and chlorine on the end. So we look here at the electronegativities. Carbon is 2.5 and chlorine is 3.0. 3.0 and 2.5. So between carbon and chlorine, if you want me to draw this separately, based on these electronegativities, if we were to subtract them, the difference is 0.5. Now remember, if you have 0.5 or greater, you have a polar bond. Okay. Next step would then be to look at the entire molecule. So chlorine is a little bit more electronegative and wants to pull the electrons with a greater force towards it, creating this partially negative end and then this partial positive end on the other end of the molecule. Well, imagine if we have that same molecule here next to it, and if we have chlorine pulling all those electrons towards it, creating this partial negative over here, this end of the molecule would have a partial positive end. And we know positives and negatives attract to one another. And this attraction is greater than London dispersion forces, which we talked about earlier, because there truly is polar bonds within the molecule pulling the electrons stronger towards each other as opposed to carbon and hydrogen in the previous example. So polar bonds, polar molecule, because the vectors do not balance out. There's one vector pulling towards the chlorine in both these molecules. Therefore, dipole-dipole, intermolecular force. Now, a special case, a stronger case of dipole-dipole intermolecular forces is something called hydrogen bonds. Okay? Hydrogen bonds has to do when there is an intermolecular force with a hydrogen to one of the most extremely highly most electronegative elements. So if we look at these electronegative values, you could see on the top right, nitrogen, oxygen, and fluorine, 3.0, 3.5, and 4.0 are the most electronegative elements on the periodic table. Okay, they really want their electrons to fulfill their octet. So if we look at water down here, if we look at hydrogen and oxygen, oxygen has a 3.5 electronegativity and hydrogen is 2.1. So between those two, hydrogen and oxygen have a very polar bond. If we take the difference, we get what, 1.4? And as long as the bond, the difference in electronegativity is 0.5 or greater, remember you have then what's called a polar bond. Okay, now we have to look at the entire molecule to see if it's polar. Okay, 3.5. So oxygen wants the electrons a little bit more, a lot more, I should say, than hydrogen, creating this partially negative end, or this pole. And then hydrogen would have this partial positive end. Same thing then if we draw it on the other water molecule down below here. Okay, so there definitely is some sort of polarity between these two compounds because the partial negative end and the partial positive end are going to create this attraction to one another. So it is an example of dipole-dipole. However, since there's a hydrogen and an oxygen, there's something special called a hydrogen bond. Okay? This happens anytime we have hydrogen directly bonded to nitrogen, oxygen, or fluorine. So it has to be a polar molecule, and you have to have nitrogen and hydrogen as a bond, oxygen and hydrogen like you see here in water, or fluorine and hydrogen. The reason hydrogen bonds are much stronger than regular dipole-dipole intermolecular forces is because you not only have such a big difference in electronegativity between this hydrogen and oxygen in one molecule, You also have it in the other one. So this partial positive end is attracted to this partial negative end, plus you have such a big difference between this partial negative end and this partial positive. There's a couple ways you can remember this. NOF, nuff said, or phone, kind of like calling somebody. Or you'll just remember because they are these top three elements here in the top right corner. So a special case of dipole-dipole is anytime you have a polar molecule. However, what makes it more special is you have that hydrogen bonded to nitrogen, oxygen, or fluorine. So just to review here, if you have a nonpolar bond, you automatically have a nonpolar molecule which has the weakest London dispersion forces, which are called London. And that's because there's just these temporary dipoles as the electrons are moving around. When you have a polar bond, which creates a nonpolar molecule, same idea. If it's a nonpolar molecule, you just have those temporary dipoles. If you have a polar bond, that create a polar molecule, you have something called dipole-dipole interaction because you have a true tug of war going towards that electronegative element. And a special case if you have hydrogen bonded to nitrogen, oxygen, or fluorine. And the last one we didn't talk about because we did it first semester was ionic bonds. The reason those are the strongest is you have a true transfer of electrons from, let's say, sodium losing its electron to chlorine to make table salt. So that is the strongest force between molecules because the electrons are actually transferred. Have a great day. Go Pirate.